Yes, sir.
Yeah, these days, every day we have a conference, either on Google or Zoom or Microsoft. So we are all familiar with the technology. It's amazing how quickly we learn all these minute aspects. So I'm going to talk to you on applications of advanced functional nanomaterials for energy storage. Each word is very important. Applications. I'm sure mostly being engineers and teachers of engineering students, you all know what do we mean by applications. Advanced is a term which you must know. Primitive. Right from Stone Age to Internet age, energy is essential. What is important is during this generation of energy, various materials are involved. Any means of generating energy, hydroelectric energy generation, or you talk about coal powered, using coal as a resource, we generate energy, thermal power station. During this generation of energy, so all these generation, we use different type of materials. When I say advanced, it means that for 1 kg of material, how much knowledge has gone inside? Wood is not an advanced material. It's a material which is there time immemorial. However, a carbon composite is an advanced material. So each word you please listen carefully. Advanced means a material which continuously evolves, new functions, maybe it becomes weight becomes less, function become more, strength become more. This is why advanced. Advanced means compared to the original material used during Stone Age or Copper Age or Bronze Age, this material has evolved by putting so much of knowledge into it. Carbon steel, modern carbon steel is an advanced material. So much we know how to control the grains, how much of the other components are going inside, how strength we can augment by controlling composition of chromium, nickel. So this is what is the meaning of advanced. Functional. Each function, these type of materials are called multifunctional materials. Same material can have different type of functionalities. Nanomaterial, being a department of nanotechnology, you know what are the benefits of going for nanotechnology, nanomaterials. How all these could be combined to get benefits, more higher efficiency without environmental contamination. This is why how these advanced functional materials could be utilized for energy generation, storage, and transformation. This would be the theme. I'm sure that you all know we are having a difficult time, uncertain time. Uncertainty is there in our life. Pandemic has created havoc in our life. At the same time, pandemic, although we have serious issues, almost several millions of people have been infected. 23, 24 million people have been infected world over, and more than 1 million people is the mortality. With such a damaging influence, we also look at from a scientific side. There are people have become more and more aware of science. People have become more and more aware of materials. Different type of materials are used to fight with the pandemic. Materials, advanced functional materials are used for making mask, 3-layer mask, 4-layer mask which allow only virus to be stopped. You can imagine, these are all interesting aspects of material. So nanotechnology is also providing so much of support for fighting with the scourge of COVID-19. You can see now people are trying to develop vaccine, a cocktail of various antibodies to prevent the spreading of these diseases. You can see now, so nanotechnology has pervaded every aspect of life. I'm going to talk to you only about the energy generation, energy storage. Since being led by nanotechnology department, I will not go to details. I'm sure that you must pay our tribute to all these great masters who were instrumental in developing nanotechnology. Nanotechnology has a clear birth date, 1959, when Richard P. Feynman first talked about plenty of room at the bottom. That is considered universally as the starting point of nanotechnology. Although nano word was not there, nano word was used only after several years, 1974 by a Japanese scientist Norio Taniguchi, a professor of Tokyo University. And from there we came up with characterization, atom level, molecule level. 1981 we had scanning tunneling microscopy, which allows you to play with atoms, write with atoms, manipulate atoms. Then soon after we had atomic force microscopy, then variants of all these. What is interesting is, all this generated so much of enthusiasm in physicists because they manipulate the interaction. They have tools which will allow you to find out 0.01 Armstrong. Extremely, very, very precise location you can manipulate. Physicists were so interested by looking at this. So study the interaction, very strong interaction, very weak interaction. Chemists were interested because they can manipulate, make new materials. All these applications are in engineering. That is why nanotech, there is no branch of science and technology where nanotechnology has created a big impact. What is unique and all these to benefit humanity? Can we use all these to solve our problems of energy generation, energy storage, and environmental degradation to prevent environmental degradation? All these are linked problems. That's why we don't look at energy technology as one branch. It is a branch with so much of continuously expanding frontiers. We need, a typical example is battery technology. You need mechanical engineers, you need electrical engineers. You want to store lithium, some material, they will expand. How do you control the expansion? How do you calculate how much with 10%, 20% of lithium ions engulfed in this material, how much expansion? Can you control them? Can you minimize them? So this is the reason why similarly there is a lot of heat generation, thermal engineering is important. This is the reason why nanotechnology, just like we talk about a multidisciplinary area, energy technology will show all these. Maybe I would say last 50 years, we have accumulated so much of knowledge in various branches of science and engineering. We have ability to tailor composition and structure from nano to meso to precise atomic level, molecular level. For example, these days, materials are designed, the structure, perovskite or spinel. You take the structure and each structure, what are the cations, what are the anions, where you want to remove one cation, knock out and put another cation to get a benefit. Battery cathodes are an example. Sometimes you put precise stoichiometry, 1/3 of the sides you substitute with a divalent ion. In a similar manner, on the surface, we can do surface engineering, create defects, number of defects on the surface. Surface states, surface traps can be artificially created. We make small quantum dots of carbon. On the surface, there are edge states. The edge states can be manipulated. So please remember that nanotechnology has helped you to manipulate matter at molecular level. System, subsystem, at the surface, absorption, where it absorbs, what are the sites available, all that can be understood by using nanotechnology. Along with this understanding, instrumentation has also reached unprecedented level. Revolutionary way. We can look at a spin of one atom, chromium or nickel or gadolinium. Sometimes, magnetic hydrogeneration, energy generation by means of many other ways. You need to look at what you call it as spin engineering. So one spin can be looked at, which was not possible earlier using what is called MFM, magnetic force measurement. So please remember that along with our ability, generate chemists to manipulate atomic and molecular level, we also had excellent advancement in engineering to look at, to probe, to image. Materials can be imaged at atomic levels. Spatial resolution can be 0.001 Armstrong. Earlier it was not possible at all. You can imagine, and the dynamics of reactions at the surface in the bulk can be imaged. In these two advances, at the same time, we also could go to computationally intense problems we can handle. We have tremendous computational capability these days available with the cloud computing, modeling and simulation. What happens at the center of Earth? We can sit here and do simulation experiments. What happens on the surface reactions on sun? We can sit here and do that. This is why simulation, experimental as well as computational length scale and time scale, how the galaxies evolve, what is dark matter, all that can be calculated because of advancement in computation. You can imagine all this converges into final benefit for humanity. Big data engineering, large data can be managed. For example, let's say how many solar power, solar photovoltaic systems are there? 1 mega, giga, all these, but small module is same. How much data is continuously coming from each of these modules? They can be analyzed with tools. So the analytics, archiving, these are all possible as a result of our artificial engineering. Expert systems are there. And these are also important for life prediction, visualization of new phenomena. Imagine all these convergence. So last 50 years, you will see revolutionary changes in computation. Laboratory changes in data analysis, artificial intelligence, and materials. All these convergence, you can see how they impact our way of energy generation and energy transformation. If you look at the global problems, humanity's major problems all of us face, energy is one of the major issues. Perennial issue, I would say that. Next 50 years, energy is going to be a major issue because without energy, there is no development. We want to make, we are more and more greedy for energy, and energy should be generated in an exponential manner because demand is increasing. Big cities are coming up, metros are coming up, new flights. Due to COVID, there is a lull. In fact, you can also, it is almost like a sarcastic to say that COVID has created some positive benefits for humanity. Number one is carbon dioxide emission has come down. Number two, many places that water has become clean. Whether it is in Europe, Rhine River, or in China, the Yellow River, or in India, Ganges, water purification has come down. Many factories have been closed due to COVID. So no, CO2, NO2, SO2, they are not coming out. So these are actually benefits because the human-made activities crippling our environment and our planet, that has become little less now. But things will continue. I am sure our progress is also impeded. Economy is again adversely affected. Look at the major global problems. Energy is number one. If we have plenty of energy, water is no longer an issue because with this energy, we can drink water. Food is again not a major issue. Once you have our energy problem solved, rest of the things can be handled. Even environment, cleanup can be done if you have plenty of energy. So affordable energy generation in small form, large form, because we need a mixed bag of energy. That's why a country like India with large population, we cannot depend only on one mode of energy. Sometimes we need from one source, another source. All these cases, we need materials. Without material, there is no way you can make energy, whether it is solar or windmills, need very nice composites, it should be there. Similarly, you talk about any other means of energy generation, we need materials. Nanotechnology has generated amazing type of materials. You can look at wonderful materials. Some of these materials are there. They are artificial materials, polymeric materials, but strength is much more than that of steel. Some of these materials have got unusual properties. You can have a Teflon coated material, highly hydrophobic, self-cleaning materials. Similarly, there are strong materials. So we would just see something about the chemistry, physics, and engineering of all these materials. Please remember, these materials these days, we can make intelligent materials, materials which can understand what is happening in the environment. So right from Industrial Revolution onwards to the present digital revolution, we always have new form of materials. Materials are artificial materials like spider silk, very soft to touch but very difficult to break. Composition wise, it is all amino acids. 95% amino acid, a small amount of 95% alanine, glycine, amino acid is 5% of calcium phosphate. But the way it is arranged is very interesting. We talk about hierarchical materials. Functional, all of these are functional materials, multifunctional. Sometimes the material undergoes change in such a way that they have multiple functionalities. For example, you have a ferroelectricity, you have a ferromagnetism. At the same time, color will also change. So you will see different type of these multifunctional materials. Some are organic, some are inorganic, some are organo-inorganic. Some of them, these materials have a iron or gold or silver at the core. And the shell, they have an organic material. Shell will get color change with respect to environment. Humidity changes, color will change. Stress changes, color will change. So based on the environmental stimuli, property of the material changes. Initially, it will be insulating. After some time, you will see this become metallic, insulating to metallic transition. So all these properties can be tuned when you make these materials. In the laboratory, when we make such materials, atom by atom, molecule by molecule, that will be done by the skill of synthetic chemists. That time, you can introduce superhuman qualities such as intelligence, such as how to respond with respect to change in the environment in a non-exponential, in a highly exponential or highly non-linear manner. We talk about designer materials. Can we design materials for our energy requirements? Can we design materials for generating energy at the same time without creating problems for the environment? These are the questions which we need to look at it. These are important because A country like India with a huge population, we are also going to embrace circular economy. What is special about circular economy is that our needs are completely fulfilled, but there is no waste, no recycling, or recycling is there in the system, but nothing will be coming out the environment. All the material feedbacks are closed loops. How does it happen? Because we need to plan it. And the entire system is interesting. This is what is important about the circular economy. We will be using 3D printing. We will be using disruptive technology. Innovation will be there always at every stage. Simulation and machine learning will be employed. This is why it is called circular economy. I'm sure that for a country like India with a huge population, this is the only way for going forward. We have around 1.7 billion people now. China has a little bit 1.84. But the energy consumed by us is very small. Although we have this 16 to 17% of the world population, energy consumed by us total is only just around, less than 7%. China, on the other hand, with 1.84 billion people, 23% of the world population is with China. They use 23% of the, 23%, but they use large amount of energy. They have, not 23, they have around 17 to 18% of the population. They use 23% of the total energy. Compared to US or Europe, per capita energy we use is very poor. That is why we have a high aspiration. Our population will become much more now. Recently, the increase is there. We are going to overtake China soon. Our government considers a 5 trillion economy by 2023. By that time, we will have almost 1.8, 1.85 billion people. The growth is considered. So there is no way that the energy demand for a country like India with a huge population, with average energy consumption very low, the demand is very high. There's an exponential need for energy. 10, 20 years back, our energy was agrarian. How much energy a person needs per day for a comfortable living. You can imagine, even now we will see many places in India, villages like this. You go, you will see people get up in the morning, they go to the field, they come back, and total amount is energy use is very small. This is in village, but you go to big cities like Mumbai here, you have 24 million people or 25 million now. City grows horizontally as well as vertically. You need, how much energy you need to give food, comfortable living, medical facilities, water for such people. City is 24 hours active. And there are several such cities in the country. Look at another city in India, Delhi, with almost 30 million people. 36 it will become in 2030. By that time, India will overtake, Delhi will overtake Tokyo as the most popular city in the world. Delhi is actually competing with two other cities, with Tokyo in terms of population, with Beijing in terms of pollution. You can imagine. So all these are issues of development. India has several other cities, I'm sure, Bangalore, Chennai, Kolkata, Pune, all these places, growth is done in only affluent sectors, and that creates so much of problem for energy. Kolkata, we still have these polluting ambassador cars. Pune, we still have number of two-wheelers more than that of the number of people, more than the population of the city. Now, how do we solve all these problems? As growth happens, this is an old image, 2015, but 2020, this is only no big change. You can imagine, a city becomes a mega city when the population crosses 50 million. You will see all these red dots. India is full of such mega cities. So how do you balance growth? Number of vehicles are increasing, pollution is increasing. India has roughly 20 vehicles per 1,000 people, and this is increasing slowly. By 10 years, 20 become 25, 30, 35. That's the reason why government is planning to have an electric mobility mission. So at the same time, our environmental, one side, our energy demand is exorbitantly high, exponentially increasing. Other side, our environmental footprint is very poor. Look at the global pollution index. All these places, India has become very poor. India has 155 last year. Now it must be worse only. China even is better, 180. This type of developmental problems need critical solutions. Solutions are there. We have to adopt it. From outside, from space, if you look at globe, you will see the brown patches are there in Africa and India. India has so much of these brown patches come essentially because of sulfur dioxide and nitrogen dioxide. They are all coming in aerosols from outside space. You look at it. So the pollution quality, what you call it as pollution index for India is very poor. These are all problems which are linked with energy generation, energy storage, and how we use energy. Energy sources can be classified into two: energy sources from hell and energy sources from heaven. So far, we have been using energy sources from hell, coal, natural gas, and they disrupt the environment. They are not sustainable, dwindling of resources on one side, then heavy pollution on the other side. They are not sustainable. It is time has come for us to focus more on wind energy and solar energy. India is doing pretty well if you look at globally. In Paris Treaty, we made a strong commitment that we will reduce our carbon footprint, carbon emission 25% by 2020, and we have done several things. Was close before COVID. We took stock of the situation. We were touching whatever we promised. The whole world, if you compare, on the other hand, they are much behind. Regulatory bodies, governments came together. They agreed that whatever we wanted, we will do to make sure that global warming is less than 1.5 degrees centigrade, if possible, at least less than 2 degrees. Unfortunately, that's not happening. India at that time made a pledge that we will generate 175 gigawatt by 2022, 100 from solar, 60 from wind, 10 from small hydro, and 5 from biomass. Apparently, this has done very well. Our renewable energy portfolio now is 22%. Out of 100 we committed for solar, almost 89 we have completed, 20 are already being installed. So our solar and wind part also we have done very well. So what happened is, last year in a global platform, by looking at the progress, government made a little more stronger, ambitious commitment. We will say that we will make 450 gigawatt now by 2023. This is interesting because India completed our world commitment about, see, we wanted 20% by 2020. That is already over from renewable. We are already 23, we are touching. Unfortunately, in the world, other countries could not come up. US pulled out from this during one of those COP meetings. Australia also pulled out. Now, without US, without Australia, it's very difficult because if you look at the worst polluting countries in the world, number 1 is China in terms of carbon dioxide emission. Number 2 is US. Number 3 is now India. European Union also went ahead very strongly. There were several climate deals, what you call it as IPCC meetings after to complete Kyoto Protocol is going to, actually it is going to expire soon. But Committee of Parties meeting in Bonn in 2017 and Poland in 24. Poland, we could not even conduct the meeting last year. To conclude this, although world countries are far behind in their commitments, except few European countries like Germany, although US pulled out and Australia pulled out, India is, as being a signatory, we are going very strongly with our commitment despite COVID. This is the reason why we are a little bit slow down in terms of the mobility mission, but we go strongly telling that 30% of all our vehicles will be electric by 2030. Initially, we get some promise which we could not fulfill. Some minister says that all vehicles will be by 2020 electric, etc., etc. But I will not go to the details. I only want to say that, look, we have already around 7 million electric vehicles in the world. India promised long ago that we'll have 6-7 million by 2020 from India itself, but we couldn't. Our total number of electric vehicles in the country will be roughly around 40-50,000 only, although we made very strong commitment. But the mission plan is on, and I'm sure you see, because there are difficulties. Being a huge country, we need various segments of energy. We cannot depend only one. Please remember that Niti Aayog statement that even in 2030, we will not be ruling out coal. So some space is always there for coal and oil. We cannot make it because being a big country with different resources, affordability, geography, location, availability of resources, that is the reason why even 2030, we will see that step by step renewable will slowly increase. We cannot rule out completely. Nuclear is always there with us. So you will see that being a big country with various geographic location, different type of people, different type of industries, this is why we cannot come out. But global challenges of controlling carbon dioxide emission, India is going very strongly. We have a national electric mobility plan. 6 to 7 million vehicles we plan to sell by 2025. Similarly, 2030, the national e-mobility program will go on very strongly. 30% of EVs will be there by 2030. Every car sold in India from 2030 will be electric. This is a commitment from our government, and our government is doing so well with several ministries aligned together. I'm sure that we will have several millions of electric vehicles, two-wheeler and three-wheeler soon. But what is preventing a faster progress, if you ask? There are several problems. Supply chain, similarly, manufacturing segment is not moving very strongly. Most of these are, people are happy to get vehicle, not only vehicle, even batteries from outside. Manufacturing part, because again, critical materials. Critical materials, generating this material from raw materials, then processing them, then the manufacturing. We look at this. So nanotechnology has made wonderful materials. Some of these materials are amazing because in terms of their performance, functionality, but most of these materials are costly. Number one problem is are not affordable. Number two, raw materials. If imagine lithium batteries, we always use fluorine containing electrolyte. Where do you get these fluorine containing electrolyte? India, nobody is making it. If all these electrolytes, chemicals should come from China only, then how are you going to reduce the price? These are all the issues. Similarly, graphite. India has plenty of graphite. But if you want lithiated graphite, lithiation should go. This graphite needs to have certain quality. This quality of graphite is not available. We have so much of graphite ore, but processing. So this is the same issue. There are critical. Can we fill these gaps? Again, the present government is very boisterous about bringing NRI with multiple skills to fill these gaps. I'm sure all these are all important areas where we'll see big changes in future. I would like to talk about nanomaterials. Some of these materials I mentioned to you, they are all materials with unusual properties, unique capabilities. Materials behave as if they have intelligence. Materials have qualities similar to what we have in human brain. Self-diagnosis, self-tuning, sensitivity, shapeability, switchability, self-repair, selectivity. As if these materials, for example, some of you must have seen a movie called Terminator 2. Terminator 2 has an artificial robot called T-1000. You put a bomb on this robot, he will explode into 2 lakh pieces. But within few seconds, they will come together, self-assembly, self-replication. These are all the qualities which we can now generate on a material. Certain materials are there. Material knows what is happening in the environment. Material changes as per the environment. We have such materials. For example, we have such, what you call it as intelligent vehicle. The vehicle has a coating. This is actually, if you look at from a very name point of view, this is a zero emission vehicle. Nothing will come out. No carbon dioxide, no sulfur dioxide, no nitrogen. In fact, this vehicle is a fuel cell powered car, which is totally green. Green is black in color, but what is interesting is the color itself you can change by sitting. So there is the color if you want red, green, blue. The coating is an electrochromic coating. Based on the voltage, the color can be changed. Aesthetics also can be controlled. Shape change, color change. If there is a small amount of humidity change, you don't need to switch on wipers automatically. So all these embedded sensors can be included along with this type of smart vehicle. If some driver is drunk, he cannot open the door. There is an alcohol sensor on the handle. You can imagine. So the automobile engineering is an area where many of these wonderful materials have been incorporated during the assembly. And some of these are for energy saving, highly efficient. I'm sure the theme is also about efficient materials. You will see energy is an area where you will see fecundity of materials with unusual properties. We talk about hydrogen economy. Hydrogen economy we have been talking for long, but now there are materials available for hydrogen storage, transportation. Only problem is where is hydrogen? Hydrogen is not available. I'm glad that some of your lectures are related to water electrolysis. Water electrolysis has got tremendous capability. Almost all hydrogen, 85% of hydrogen now manufactured in the world by steam reforming. That means fossil fuel, which is not acceptable from an environmental point of view. We don't want CO2 at all. So carbon neutral hydrogen generation is important. That is electrolysis. Unfortunately, electrolysis is more expensive. Sometimes people use platinum, iridium, very expensive materials. This is the reason why I mentioned to you, every technology, energy technology, there's a critical material which is needed. And these materials are mostly not affordable. If you make such affordable materials, then energy generation becomes easy. Again, I will skip. There are several such materials. Some of these are intelligent materials, wearable electronics. Also, there is an interest because small power sources. We don't need big energy. Very small energy is needed. There are shirts which can absorb sunlight, generate energy, operate a fan on the shirt. We have some, color of the shirt also can be changed at your based on your interest. You make a green shirt, red shirt, blue shirt, etc., etc., etc. You may have a small electrochromic wearable conducting polymer based shirt. You have a small battery in your hand. You can keep 1 volt, color will change, 2 volt, another color will change. Small PV module can be flexible. Solar cells can be incorporated in the shirt. So you will see such a disruption all due to materials. Some materials will help you also to make artificial sensors, artificial noses. Again, I will not go to detail. I only want to tell you that there are plenty of such materials. These materials are important because they help you to generate energy, they help you to store energy, and you will see revolutionary changes in the way we generate energy. And they could be connected with grid. We have several programs on smart grid. I'm glad there are lectures on smart grid. Smart metering is important again in the area energy landscape. So energy landscape, you look at it, you must look at solar energy, you must look at wind energy, you must look at these are the generation, and you must also look at fuel cell and hydrogen economy. All these are generation technologies. There are also solid state generation technologies which are important, but cost wise they are not very affordable. Then comes storage. Electrochemical energy generation and storage has an advantage because when you convert free energy of a chemical reaction into electrical form, it happens directly. That means there is no Carnot limitation. The second law of thermodynamics is not valid because of direct conversion. So efficiency can be very high. When you combine this along with heat, what is called cogeneration, efficiency can be still higher, 88, 90%. That's the reason why solid oxide fuel cells where energy is generated at 800, where the efficiencies can be extremely high. Cogeneration gives you sometimes 90%. Unfortunately, solid oxide fuel cell, again, there are other issues, high temperature corrosion, material problems. That is why it is not again affordable. There are people, there are countries where solid oxide fuel cells are shown. California, for example, there is a company called Bloom Energy. They have solid oxide modules for residential purposes. 5 kilowatt, 10 kilowatt, 20 kilowatt. But you can't compare them with respect to the normal grade because it is more expensive. But the environmental point of view, they are important systems. Similarly, there are polymer electrolyte fuel cells, which will allow you to have a fuel cell powered vehicle, more expensive than a lithium-ion battery car. So look at the materials on display. Battery materials, lithium batteries, sodium batteries. I'm glad that you have several lectures on this. Solar, photovoltaic materials, dye-sensitive solar cell, perovskite solar cells, organic solar cell. Efficiency may not be very high, but you can print them just like a inkjet printer. 3%, 4% efficiency is also okay, but they are very cheap. Electrocatalysis for water electrolysis, for fuel cells, hydrogen energy, redox flow batteries. All these cases, thermoelectrics, a very important area again. You will see that materials availability has made significant change during last 30, 40 years. Along with materials availability, modeling and simulation using computational tools. So I mentioned to you about electrochemical energy generation. We call them as electrochemical power sources. And what are electrochemical power sources? Electrochemical power sources are engines where free energy of a chemical reaction is directly converted into electrical energy. So the conversion is direct. There is no PDV term. That means the limitations of Carnot cycle doesn't come into picture. Efficiency can be intrinsically high. This is number one advantage. Number two, this energy generation is intrinsically clean. There is nothing coming out. Imagine hydrogen and oxygen coming together to form water and electrical energy. Delta G is converted into delta G naught is converted into delta E naught. No, it is a silent energy, so no pollution at all in principle. So we can look at three advantages. Number one, efficiency is very high. Number two, environmentally, it is much more cleaner. Number three, modularity. Small system, big system. For wearable electronics, I need few milliwatts only. For a power station, I need gigawatt or megawatt. Load leveling, This is what we talk about modularity. So I can talk about several such advantages. At least 3 or 4 important advantages of electrochemical power sources compared to other things are that there is no ecological restriction. Unlike hydroelectric, you need large area that is not needed. Number 2, it is modular. Number 3, it is internally clean. Number 4, high efficiency. These electrochemical power sources can be roughly classified into 3: batteries, fuel cells, and supercapacitors. All these 3 common elements, common terms are there: energy density, power density, cycle life, rate, self-discharge, shelf life. These are all important matrices to compare the performance of these devices. Batteries can be further classified into primary and secondary. I'm sure rechargeable, you know about it. Fuel cells are entirely different systems where environmental footprint is very, very clean. Battery, they have a problem because batteries need to be recharged. Recharging environmental footprint depends how you generate electricity. If electricity is generated by coal or thermal power station or any other means of fossil fuels, then even your lithium battery for electric vehicle is not going to help. It is not going to change the environmental footprint. Fuel cell, on the other hand, problem is hydrogen availability. If hydrogen is obtained from solar or from wind electrolyzer, then fuel cell is much more greener than battery powered car. A fuel cell powered car is much greener than powered car. But batteries and fuel cell, they have a problem. They have very high energy density, but the power density is very poor. That's the reason why we talk about supercapacitors. Batteries and fuel cells are good for storing energy, but when you want bursts of power, either to store or to retrieve, they have a problem. They have very poor power density, very high energy density. Supercapacitors, on the other hand, they are complementary devices. They have high power density, very poor energy density. So if you have a combination of supercapacitor with the batteries, supercapacitor with the fuel cells, that is what is needed. People use an organ diagram to compare their performance, energy density versus power density. Batteries are available for donkey's years, and I will not go to details. I'm glad that there are much more competent people in this program. They will be talking on several types of batteries, cathodes for lithium batteries, supercapacitors, etc., etc. But you must only keep it in mind that nanotechnology has provided long-lasting benefit to this area. Why do I say? 10 years ago, cost of lithium-ion battery was extremely high. In 2008, it was $1,000 per kilowatt hour. Now you get around $150, $120 per kilowatt hour. The exponential decrease price of a battery per unit power with respect to time, you can see very exponential reduction. Same thing happened in solar photovoltaic. Now solar photovoltaic, you will see so many panels. Every engineering college has a solar photovoltaic on the terrace. This is mainly because of the cost reduction. Amazingly, same level of cost reduction you have seen in lithium batteries. What was there in 2008 and what is there in 2018 or 20, you can see now. We have almost, and Tesla predicts that we'll touch $100 per kilowatt hour. Why did it happen? Mainly because of nanotechnology. Nanotechnology has given so many materials and the performance has been sharpened at various levels. We still have a lot of problems because some of the cathodes are battling for supremacy for electric vehicles. Market is so huge that there is so much of money, and the corporates, government, they are all so greedy that they fight with each other. Whether LFP, lithium iron phosphate, whether lithium manganate, lithium nickelate. Some people say, I don't want cobalt. Cobalt has a very poor environmental footprint. But again, I will not go to details because all these are all going to be talked by many of our scientists in these few days. I see the titles of many of these programs, and I see that they are all going to explain to you at greater details. There is one lecture on lithium battery, cathode, another one on electric vehicle, either from SICRI or from ARCI or from IT Madras. They will talk to you more details about it. I just wanted to give you a feel that the exponential reduction happened in solar photovoltaic, same thing happened for batteries, and still we have problems. There are important research areas in lithium-ion batteries with respect to materials, conversion electrodes, than the conventional intercalation materials, new type of electrolytes. Everybody uses the same electrolyte, but people want different, more cheaper, more long-lasting materials. Similarly, where is lithium available? There's a lot of debate on lithium resources, and many people believe that sodium will be the battery for soon going to be for electric vehicle. storing lithium itself, several options. Lithium in carbon, lithium in silicon, lithium in aluminium, I'm sure alloys. These are all topics where you will be listening from various people. One thing is sure that as time goes on, we'll come up with newer and newer innovations. Everybody is thinking about an all solid state lithium batteries or even sodium batteries. No liquid electrolyte. The explosion problems, safety problems are more because of the electrolyte. If you get rid of the electrolyte, self-discharge will be less. You don't need a separator because this will be the electrolyte itself is a separator, solid electrolyte. So people, next generation batteries, people think about all solid state batteries. For that, several consortiums are ready. Some consortium only in Japan, Toyota, Nissan, Honda, Panasonic, they come together. They say that, look, we want the Japanese dominance in this area to come back. So they have a consortium. Many other advanced battery consortium is there in US and Europe. Several programs are there. The science is also very interesting. It's not just materials and its application alone. Science is very interesting. One evidence is that last year Nobel Prize was given in this area for a team of 3 people. You can again see the relevance of engineering here. Nobel Prize in chemistry goes to 3 people. John B. Goodenough, University of Texas at Austin. He's a condensed matter physicist. Stanley Whittingham, Bingham University, State of New York. He's a chemist. A mechanical engineer, Ashaki Kassim Corporation. Hello? So you know, a team of 3 people got Nobel Prize last year. This year Nobel Prize is going to be announced within a couple of weeks. Akira Yoshino is the youngest, born in 1948, mechanical engineer. But why did he get Nobel Prize? He worked only one material, carbon. He somewhere read Goodenough's an article, used lithium cobaltite as a material, but he wanted to store lithium. He knew that there were several explosions due to the way of storing lithium as a metal. His only contribution is he worked in an industry, worked so many years only on one material, carbon, petroleum coke, different type of coke. But he came up with a model of lithium batteries which Sony could commercialize, IISER 1991. So the first lithium battery commercial production happened only because of Akira Yoshino's insight on materials. He is a mechanical engineer. He got Nobel Prize in chemistry. Now you can imagine Stanley Whittingham as a chemist. He did PhD from Oxford. He was a postdoc in Stanford University. After a postdoc, he worked with the solid state battery, ionic dynamics, movement, solid state ionic conductors. And he went and worked in again one company. Actually, when he was a postdoc in Stanford, ExxonMobil, oil giant, the energy crisis was just looming, 1970, 73. They went and recruited this bright postdoc from Stanford, asked him to make batteries. He kept on making batteries for 16 years there, only using sulfides, titanium sulfide, iron sulfide, chromium sulfide. Interestingly, he coupled this with the lithium metal, and all these batteries exploded at various stages. So after 16 years, company found he's of no use. He has only created thousands of explosions. They sacked him, and then he came to Bingham University as a professor. You can imagine, and he gets Nobel Prize because of his work. His work is essentially, he is considered as father of intercalation chemistry, lithium titanium sulfide, lithium niobium selenide, all. But imagine, he got Nobel Prize at the age of 78. And now we have got John B. Goodenough at the age of 98. 97, he got Nobel Prize. Now he's 98. You can imagine the relevance of teamwork. One mechanical engineer, one chemist, and one solid state physicist coming together with amazing quality of materials. This is the primary reason why we are all using lithium in our mobile, in our laptop, in all these applications. Battery technology's history is very, very interesting. A lot of corporates come into picture, a lot of greed, a lot of cheating, all that happened. If you look at it at some other time, I would be able to talk to you. Let me just wind up the talk. There is a road to super batteries for tomorrow. We know what are the parameters. Many of these parameters would be touched up by speakers following me in various lessons. 250 watt-hour per kg, 650 watt-hour per liter, how many cycles, all these are very, very clear. Lithium sulfur, lithium oxygen, these are all the future batteries, and hundreds of startup companies are formed for this. In a similar manner, fuel cells are very interesting. Actually, fuel cells are one step ahead of batteries in terms of the carbon footprint. Unfortunately, little more expensive. Again, the issues are materials. We need a very strong proton conducting polymer. Some of these fuel cells work better at higher temperature, 150, 160. Fabrication issues, durability issues, stack engineering. Engineering plays a very critical role to couple these small modules, membrane electrode assembly, to make a 1 kilowatt, 5 kilowatt, 10 kilowatt system. There are durability issues. Again, very interesting programs are there for materials. We need composite materials as composite electrolytes, much more long lasting. We have done some work in this area. I will not go to details. I would say that we made some composite materials which are functioning better, but they're all in small labs. When you go and scale up it in larger stacks, 1 kilowatt, 5 kilowatt, we have been working with 3 industries in this area. First work was with the Reliance Industries to make a stationary power source for 3 kilowatt, 5 kilowatt for their towers, communication network. Then we had a project with the Thermax to make it for, this is a high temperature fuel cell, and another one with KPIT for a small car. So we have done some work in this area. Again, I will not go to details. What happened is that all this, even with industry support, is very difficult to commercialize. There are hundreds of issues. We can make an interesting material, replace them, get some global recognition material, but manufacturing is a different type of environment. It's not very easy. We need huge consortium of public-private partnership with more and more, government support for at least initial time, just like a mobility mission. Now, I'm sure that you will see in the next few years so much of change of lifestyle with respect to power sources. Already you can see last 5-10 years back how much mobile itself you can consider as an example. How much the power source, the design, the thickness, the weight, the space, how much it has improved. Every time, laptop 5 years ago, you cannot continue for 2 or 3 hours. Now, some of the laptops will function for 7 hours, 8 hours without recharging. That means energy stored. Now, both geometrically as well as volumetrically, you are able to have a much better performance. More and more efficiency has come because of materials. Cost is still an issue. Again, this is one of the last, maybe another 5 minutes I wind up. Cost is still an issue with respect to electric vehicle, whether it is battery powered vehicle, fuel cell powered vehicles are much more costly. Safety, life, energy, all these can be, you can see the confluence. Again, machine intelligence is going to play a critical in the way these power systems are going to be developed and deployed. The first book written by machine intelligence is in the area of lithium-ion batteries. You'll be able to get this. And each state has come up with their own mission plan for electric vehicle. Electric vehicle is somewhere we are wedded. It cannot come out. We cannot have a thing about diverse now. Every state, the states are, they have their own policies. In state governments like Bihar or Karnataka or Tamil Nadu, they all have their own policies to promote electric vehicles. There is also a very healthy environment, just like Atal Innovation Center, we have been talking about it, public-private partnership. There are several such startups available globally. Even India, you can see all these in Noida, in Chennai. There are a small segment of companies, new entrepreneurs, angel investors. They are coming up in collaboration with the scientists and technologists to form startup. How many of these startups will survive is a different matter, but as we progress continuously, we need such support. And I'm sure that the government has a very healthy policy to support such a startup. Chennai itself, Chennai and IIT Bombay and IIT Madras, there's a local environment where there are funds available if you have got a bright idea on this area. With this, let me just summarize. I hope I have given you a feeling how nanotechnology has helped energy generation and energy storage using materials. Some of these materials are routine materials with change in composition and engineering, their defects and emphasis. Some materials are totally new, composite materials. But there is no doubt that material development has illustrated the power of nanotechnology. Solar and wind case one, especially solar cells, and batteries another one. Fuel cell also in a similar manner. These days we can make a fuel cell without platinum also. It is possible. Of course, when you want to have a large scale application, there are issues. I'm sure that many global companies are eyeing India very carefully, including Tesla, some of the world giants. Probably it's a matter of time. Government also has taken very positive steps Government wanted first batteries to be imported and second stage batteries to be manufactured, third stage including our own materials. I'm sure that we will see big changes in next few years, and we need all the branches to come together. Physics for instrumentation, for understanding the interaction, chemists to skill these to make these materials in a skillful manner, and mechanical engineers, electrical engineering, because power again, electric vehicle also there is a DC motor component. So all these programs will, we hope India will move on a faster track towards prosperity despite temporary problems of COVID. Again, I just would like to thank all of your patience by making a statement from Thomas Alva Edison, who was inventor of many things. Among other things, he's also one who was very passionate about batteries. Nickel-ion battery was invented by him. Storage battery is, in my opinion, a catch penny, a sensation, a mechanism for swindling the public by stock companies. Talking about greed between companies. Storage battery is one of those peculiar things which appeals to the imagination, and no more perfect thing could be designed by stock swindlers. Like, this is all the more important for lithium batteries because there were several cases against big corporates to claim for the profit. With this, let me thank all of you for your patience, and if you have any questions, I would be happy to answer. Thank you all.
Okay. Thank you, sir. Thank you for your wonderful lecture.